First of all, I apologize if this looks like this is too small. We tried every which way, and this seems to be the most effective doing it in this whole room. And secondly, I want to thank the organizers. I have lost the count of I have been to this institute so many times. And Schwermer has been the host all the time, both as a director, as an organizer. And it's a wonderful place to be, and I really appreciate it to be invited again, even in this age. All right, let me start with this talk. All right, F is a local field, either real or periodic. G is a connected reductive group. I'm assuming it's quasi-split over F, things become a little easier. W prime of F is the Freydoon group, and G check is the complex dual of the group G. Wow, I touched the wrong thing. Okay. And the local Langlands, you of course, when LG is just a semi-direct product of G check and the Way group, the weight acting on it. And you don't need SL2C if F is equal to R. I'm sure everybody knows this, but I'm going to repeat what's the local Langlands correspondence. You look at admissible homomorphisms from W prime of F, which is just the Freydoon group, into the L group of G under the G check conjugation, meaning that all those homomorphisms whose values are conjugate of the fixed one are going to be in the same class. These are, the conjectures that these are in one-one correspondence with finite sets of irreducible admissible representations of G of F up to isomorphism, which is called an L packet. Yes. It is no, yeah, it's just yeah. Mm-hmm. But what do you impose on the quotient of alpha to? I don't think there's anything. I don't think there is anything. All right. And these are called L packets. There is an enhanced version of this local Langlands correspondence, which I'm going to mention next. And this is by fixing, you basically take the center of the G check, and you define the S of P to be the centralizer of the image of W prime of F inside G check by means of G check. And this is called the S group. And then you don't use this, but you can, this could be an infinite group. You look at the group and divide it by its connected component, and the gamma, the Galois group fixed points in Z of G check. So this is called the component group, and the enhanced version is that things have become one-to-one to elements from the parameters to a given representation in the L packet by means of representations of this component group. So then you can do it like this. Now then an LLC becomes a one-one correspondence with irreducible representations of G of F, and in each packet, which are now they can be parameterized by the representations of this component group S of phi. Now this is the set of all the irreducible representations of this component group. So in this fashion, you can given a homomorphism, you can go to each representation by fixing each individual representation of G of F by fixing a representation of the component group. This is called enhanced Langlands correspondence, and this makes things one-to-one. Now, we call it L packet tempered if it has members. If its members are tempered representations, and that would be equivalent to have this phi a bounded homomorphism. Now, there is this conjecture which has been quite useful, which I made it in my 1990 Annals paper, It's called, I called it tempered L packet conjecture. It was called generic L packet conjecture, it's called Shahidi's conjecture, all of this. It says that tempered L packets have a generic members, i.e. there is one with a Whittaker model inside every tempered packet. And it was proved by Wogan and Carlston for real groups, and then it is true, I mean, so far as we have checked it, it's true for a lot of cases in PID group, classical groups. And Michael Harris was telling me that it's true for, you can prove it over function fields if you assume everything about the trace formula for function fields doesn't exist, I mean, stabilization and all of that. Now, one thing is that if you believe in this conjecture, then you can do conjecturally extend the Langlands Shahidi to the arbitrary representation, because in every packet, there is a generic one, there is a theory for the generic one. You expect that all the other elements in the L packet are going to have the same root number and L functions. So theory of L functions would be the same, whichever. So there is not, you will not be getting something new. But so long as you don't know these things, it's of course out of reach, but conjecturally it can be reached if you believe in this. Yeah. I mean, if you extend it, and the whole idea. Another question, sir? I mean, the goal of this talk is to extend this conjecture to non-tempered representations. Okay, so now, let me make some remark about these different conjectures. LLC naturally sets up a way of relating arithmetic data like Martin root numbers and L functions to those representation theoretic data on G of F. If you somehow define a theory of L functions for G of F, this group G, F points of this group G, or its adelic group, then this thing will, as soon as you have such a thing and you have cases of functoriality, you can prove nice results about the Artinel function. For example, we know that if you take two-dimensional representations of G of the Galois group as satisfied by Langlands, this was proved by Langlands, tunnel, and this stuff, then you can prove all nice results about these two-dimensional L functions of the Artin group, of the Artin L functions attached to these two-dimensional representations. Now, if you assume that, and if you have some cases of functoriality, you can prove some nice results about more exotic L functions than just a standard one. For example, in our paper in the work, Kim and myself, we proved things about the six-dimensional L functions, symmetric powers of L functions. We showed that, they are homomorphic, or we computed the poles completely. So if you have the local Langlands, you can just take representations at L functions and root numbers at each place and look at the product, and then you can really prove that these things are nice. These Artinel functions are nice using functoriality, because then they go to L functions, which we know from automorphic methods that they are nice. Another consequence of the tempered L packet conjecture is that together with a uniqueness statement, which is now established and proved in many cases, a unique generic one can be used as a base. Can be used as a base one. It can be one which is attached to the one-dimensional representation, the trivial representation of S phi. So if you know there is a generic one, you make this enhanced local Langlands unique in the sense that you will attach the generic one to the trivial representations of S phi. So these are some nice properties of knowing this conjecture, besides other things. And then, of course, there is a lot of consequence of knowing theory of generic representations. It plays fundamental role in the work of Jacobi. Plays fundamental role in the work of Jacobi, Piotrowski, Shapiro, and Shalaika on GLN, and also in the Langlands Shahidi method. Its applications in establishing properties of L functions, functoriality, representation theory groups over local field, and the role it plays in the Authors endoscopic transfer for classical groups. This is through the work of these 6 authors: Toby, Gan, Ichino, Kaleta, Mingoes, and Shin. They have proved the A25, A26, A27 of Arthur, and now everything is modular something about the weighted orbital integrals. They have proved everything that was needed in Arthur's project. So Arthur's project is seamless now. So, you agree?
I'm sorry.
The Arthur's project is now on. Yeah, what I mean. That has been around as long as I remember. It's you guys are working on it, the French are working on it, right? So who's going to do that? All right. I'll tell them. The goal of this talk is to generalize this generic tempered packet conjecture. Now let me start with some work of Langlands and Walsberger, because this thing in a way connects to the issue of wavefronts for the representations. And the wavefronts for representations was basically came out in some way out of their work on this degenerate or generalized Whittaker functionals. Now, so let me start with telling you something about Langlands-Walsberger's generalized Whittaker functionals. One more. Okay. So let me motivate a little bit. I mean, if you have a generic representation, we all know that I'll do it after this, because this is already a preparation for what I want to say. Now, their work somehow connected lots of things to the wavefronts of the representations, which I'm going to explain now. There is this Harishchandra, how local character expansion, or irreducible admissible of G of F, F p-adic, then there exists a neighborhood U of 1, such that for all the F in smooth compact supported in U, trace of pi of F, which is just trace of integrating F against pi over, and F is compact, so this converges. This thing is given by this sum over nilpotent orbits, F orbits, of the Fourier transform of the nilpotent orbit, which I'm going to explain now, and some constants in front of the CO of pi. Now, this thing here, this object here, is that you first take the function f tilde, which would be just if you take f composed with exponential, and this is something on the Lie algebra, it's a vector space, we take its Fourier transform, and d mu of O is a measure on the nilpotent orbit, and you integrate this. So they prove that this thing holds in a neighborhood of a local character expansion. This was done, this was done a long time ago, but it has been very influential in what we do. Now, there is closure ordering between orbits. If some unipotent orbit is O prime, is less than or equal to O if O prime is contained in O bar, or closure, or it's the same thing. And clearly it says, you could have two orbits which have no relation with each other, but if it happens that one appears in the closure of the other one, if it's smaller, it will appear in the boundaries, closed orbit lemma, and all those stuff, then we will say that O prime is less than or equal to O. Now, wavefront set of pi is the set of all those nilpotent orbits of highest dimension with this ordering, which appears for which this constancy of pi is non-zero. So this is sort of gives you the singularity. That's the word wavefront comes. When you are dealing with the real groups, that's where the wavefront comes. And here, for a p-adic group, you have the same notion. And, and this is the definition. Now, the significant about being a generic representation is that you can see what its wavefront is. For a generic representation, wavefront is the regular nilpotent orbit. And this was proved by Rodier many years ago. So for a generic representation, the wavefront consists of the only regular orbit. You could have a bunch of them, but Now, what Mugdan and Wolfsberger did, they extended this idea to arbitrary representation. They tried to see what is it that signifies arbitrary representations, and how can they connect this Whittaker functional stuff to a wavefront of the representation. So let me explain. It's a very nice and cute thing. If you take an nilpotent element f inside the algebra of G of f, you're assuming it's nilpotent, and assume we have a one parameter subgroup from f star to G of f, which satisfy this thing. You take add of phi of s at f, this f guy that we fixed here, it does s minus 2, s to the minus 2 times f. Now, I'll do an example after this. For each integer, it doesn't have to be positive, let Gi be the Si eigenvalue, eigenspace of the add of phi in G. So for each I look at all those when this action gives us s to the I. Of course, these things give us for I equal to minus 2. Right? Now, let me put U to be, the usual nilpotent, maximal nilpotent, all the composite of GIs, direct sum x plus direct sum of GIs, when I is positive. And U prime to be just those which are bigger than or equal to 2. Now, the difference between these two plays a role. If, let me put F pound to be all the elements in the Lie algebra such that for all elements Z in G, trace of f times x and z, Lie product of x and z is 0. Okay? And you defined U double prime to be this exponential of this, the algebra, and times U prime. And this thing, this is U prime. The point is a U double prime. So we have a U, we have a U prime, we have a U prime, and you have a U double prime. The whole issue is whether, U double prime, of course, is bigger than U prime and is contained inside U. The whole thing is if this U double prime becomes equal to U prime or becomes equal to U. Okay? So that's how you get either a functional or a Heisenberg representation. Now, given gamma in U double prime, we define the character psi f of gamma to be psi of trace of f times log of gamma. Now, this is the character of U double prime. The character of U double prime is trivial in this part, this extra part here for G1 intersection F. So it is trivial really on U double prime divided by U prime divided by U double prime. Now, psi is a non-trivial character of F, and then one defines a twisted Jacquet module for W. W is the space of pi. Now, okay. Now, we define W double prime of F to be just a usual twisted Jacquet module. So this is going to be, you divide this by pi of U, remove from it the action of the character psi f of U times W, all the W in W and all the U in U double prime. Now, we will say that pi admits a generalized Whittaker model if f and phi, if there exists an f and phi, or with respect to this as an f and phi, W of U double prime F is non-zero. The remarkable fact is that they showed for no matter what representation is, you can find this f and phi so that that thing is non-zero. Okay? Now, with this thing, you either get a functional, just like a Whittaker functional, or a Heisenberg representation. So let me take here W of phi of F, I'm going to put it equal to W of U double prime and F, and U double prime is equal to U, or equal to half of U W U double prime F with zeta here. Now zeta is the Heisenberg thing. So if U double prime is different from U, then U divided by the kernel of psi of F is a Heisenberg group whose center is U double prime divided by the kernel of psi of F. Now this zeta is just a one, a Heisenberg representation is given by central character. This zeta is equal to zeta attached to psi F is a representation of this guy, and the center of this guy is this. So zeta F is a character of this, as I have been discussing. And central character is psi F. This in particular implies that this thing is a U module. What is that example? Somehow it doesn't show in here. Anyway, let me write it on the board. Get those examples. Suppose you are in GL3. Is this port better to write? Suppose you are in GL3. And suppose, let me take F to be equal to this important element. 0T 0, 0, 0, 0, 0, 0, 0. And let me take, if I want to produce, I want to produce an S minus 2 on T, then I'll take phi of S equal to S minus 1, S and 1. Take phi of S equal to this. And then you can see that U prime, which is the S2 eigen space is going to be just 1 something here, 1 0 0 0, and then 0 0 1. Okay. And it is equal, and F pound is, I don't have to give you the F pound, but F pound intersection G1 is just going to be equal to 0. And then U double prime is equal, U of course is 1, 1, 1. U double prime is this, and U prime and U double prime are equal because there is no intersection, and this is a Heisenberg group with this center. This is in a case of a irregular, the one above the one below the regular thing. Now, if I take F equal to 0, T 0, 0, 0, 0, 0, U 0, this is going to give me the regular orbit. And in this case, I have to take phi of S. The diagonal of S inverse S inverse. And then you will see, then this will be S minus 2 eigenspaces. And if I take diagonal, this will make it. This will do it on this element. And then you can see that you will see that U will be 1. Because on these two spaces, it's going to act like S to the minus 2. And this will be your U. And then U prime is going to be U prime and U double prime, because there is no longer, there is no S1 eigenspace. Look at it, then you take this thing and you act on the nilpotent orbit. There is no S1 eigenspace. There is no way that you can get an S1, then U double prime, and so U double prime and U prime are equal, and they are equal to all of you. Okay, so in this case, the U prime and U, they are just going to be 1. So this is the conjugate of the maximal unipotent element. And in these two cases, you can easily compute these things. It's a very simple, nice, cute calculations, and you will see what would be these groups U and U prime. Well, let me go back to normal life. Good. Is it this one? Okay. Now, I wanted to do this example. It should be here somewhere. Maybe it is, or Now, what did Muglan and Walsberger prove? They showed that maximal nilpotent orbits for which there exists a phi and there exists a phi and an f such that Muglan and Walsberger tell you that maximal nilpotent orbits f for which there exists a phi such that the w of f and phi is non-zero are in one-one correspondence with the wavefront of this representation. So the largest nilpotent orbits appearing in the character expansion with non-zero coefficients. Those are called the wavefront of f, and the maximal nilpotent orbits f, which are giving those forms are exactly those for which w of phi of f is non-zero. So this basically tells us that you can get a model for any representation, for any local representation. And some of these, models we have, I don't know, Bessel and so on, or some, some larger version of these things. You take the normalizer inside the group and things like that. And that gives us some of these models. And of course, you have the reciprocity law here. This home is equal to this home. And let me go back one more page. If you remember, I defined this w phi of f is either this thing, if u double prime is equal to u, which is just like a functional, and this one is just a hom. This object is going to equal to hom of u to here. And then you have the reciprocity, you will see that this hom is exactly equal to this sum is you will see that this hom is exactly equal to this w phi f that we defined earlier. Now with this thing, so we have a good motivation to use their ideas and to use the wavefront sets to study representation theory of these things and to see if there is a representation is generic or is not in terms of the functional, but rather in terms of the wavefronts of these representations. Now, so what I like to do in here, the goal is to generalize this, extend this generic tempered packet in two different ways. Now that was about tempered ones, so you can extend it to Arthur packets, which I'm going to define quickly for classical groups. This is so-called Jiang's conjecture, or you can extend it to the duals of the packets. This is Aubert-Jelinsky dual, which is a conjecture that Hazeltine, Liu, and myself and Lowe have done. Now, let me talk about Arthur packets. I don't know how familiar you are here with Arthur's theory. Let me define what Arthur parameters are. What Arthur did, he took the W prime F, the Freydoon group, and added another SL2 to it. So there is one SL2 which is called SL2 Delene, and one SL2 which is called SL2 Arthur. And the goal is that he wanted to parameterize all the representations, tempered or non-tempered, using these parameters. So these are maps from this triple groups to LG, to the L group. And suppose I have since the theory at the moment only exists for classical groups in any usable way, let me assume that we have a quasi-split classical group over F. Let's write this psi as a direct sum of the irreducible pieces. Now phi I is just a representation of WF. It's a bounded and containing only semi-simple elements. SMI and SNI are representation of SL2C, algebraic representations of SL2C. So symmetric powers. So SL, which L will be MI or NI, is a reducible representation of SL2C of dimension L. Now L is either MI or NI. Now we want to put this in the form of a partition. So that we take Ki to be the dimension of phi I, AI to be Ki times Ni, and Bi to be Ni. Then of course we have that sum of these things is going to be equal to N sub N. Now N sub N is 2N plus 1 if G is SP2N, and it's going to be 2N otherwise. Moreover, you may assume that these B1, B2, these are in a decreasing sequence. B1 is Bn equal to B2 all the way to Br, and then you can have a partition pip psi to be B1, A1 times, BR, AR times. So this gives you an nilpotent orbit, an N. Okay? In GLN, you can easily see this is really this is the Jordan decomposition. All right. I jumped. Now, we also define, when you have an order parameter, you can define a quasi, you can define a quasi character, you can define an infinitesimal character attached to it. So phi psi would be a map from the V group to the L group. So it's defined by phi psi of Wx is phi of Wx, and then diagonal of W to the 1/2 W to the minus 1/2. So this would be an element in the Arthur group, and then phi of that. Now it can be checked that psi going to phi psi is an injection to the L parameter. So this is an L parameter. An L parameter is from the WF to the L group, and then you can check that this thing is an injection. So these are a subset of all the L parameters, a small subset of all the L parameters, but they are very important in what Arthur does. Now, Arthur defined using his trace formula Arthur packets, which we denote by pi of psi. Of course, it is globally, and then you can restrict it to the local cases. And a collection of irreducible unitary representations. It's important that they are unitary representations. Inside this packet, it's fine. It's a local components of the global Arthur packets, which you used in doing this endoscopy. Global Arthur packets are disjoint, but local ones may not be. So local ones just come as a local component of the global ones. Now, let me take pi of phi psi to be the L packet attached to phi psi. Phi psi was an L parameter. We know L packets, so this is the L packet attached to it. Now, pi of phi psi sits inside pi of psi. It contains its most non-tempered elements. Right? Let me now take a representation pi in the packet, and let me look at the generic geometric wavefront set of pi. I'm going to put a bar in here, and this is all the nilpotent orbits in W for the wavefront of pi under the adjoint action of G of F bar. Now, this is you take the algebraic closure, and you let this thing act on the wavefront. So this is called geometric wavefront. It puts some of the rational orbits into something over F bar. Now, Barbash and Vaughan defined the duality map, which we given it a D of PV. It's a set of this D of PV sends the nilpotent orbits in G check of C to those in G of F bar. So this is a map from the nilpotent orbits in the G check of C to the geometric orbits. So those defined over the algebraic closure, geometric orbits of G of F, G of F bar. All right. Okay, let me do an example of how this thing is done. Take G equal to SP2M, then G check of C is just SO2M plus 1. Let's take this partition B to the A, so BA. BA times, like a column, and then 2N plus 1 is equal to AB, so you conclude that A and B are both odd, which through the Jordan forms gives you an nilpotent orbit in SO2N plus 1C. Okay? Then if you take dB of V, there's a rule to do it, it's not hard. It will turn out to be equal to the partition A to the B minus 1, A minus 1. So the only odd element there is A, the only odd member is A, and A is appearing with even multiplicity. So this is really an nilpotent orbit in here, B2N of F bar. Now take an R2 parameter psi, let O psi be the nilpotent orbit in G check of C containing the image of the nil positive element in SL2 A of C. So you take the R2 SL2 and you restrict your psi to that. You find a nilpotent element in here which comes as a nil positive element in SL2A. 1101. Now, similarly, you can do this for any L parameter. You can take phi to be any L parameters, and you can do this. Okay? And you can then again define O sub phi to be an nilpotent orbit in G check of C containing the image of the positive element, this time in SL2D of C under phi restricted to SL2D of C. All right. Okay. Now, one thing that we should note that the restriction of psi or respectively phi to SL2A or respectively SL2D gives the SL2C triple, providing the corresponding geometric nilpotent orbit. It's just a formal thing, but it is what it does. Now, the first generalization of the conjecture is due to Jiang. This is Jiang's conjecture. Let psi be an ortho parameter, and pi psi to be the corresponding A packet. So you take all those which are attached to psi, and for a pi in pi psi, and any O in geometric orbit in the in the wavefront set, geometric wavefront set of pi, then O has to be less than equal to the Barbash-Vogel transfer of O of psi. We have psi, we got a nilpotent orbit in G check of C, and then we apply this Barbash-Vogel operator to it. It gives me a nilpotent orbit inside G of F bar, geometric orbit inside G of F bar, and then this O guy must be bounded by this. So it gives an upper bound to the wavefront set. And the fact is that it is, in fact, you can effectively get one. This is usually hard to get. There exists at least one representation in the L packet, in the A packet, such that it's nilpotent on its wavefront set is exactly this guy. So you reach, using the representation, you reach this. Now, this is the version due to Jiang. Now, to explain the generalization, let's recall the so-called Aubert-Jolovinsky dual. This is an involution on the set of all the irreducible admissible representation. It will send A packets to A packets, and it plays a central role in Arthur's work. Now, this is not true about L packets. It doesn't set L packets to L packets. Now, let me denote this involution by pi check. So pi going to pi check denotes this involution. Now, given an A parameter psi, we can define a dual parameter psi check, just interchanging x and y. Psi check of wxy is psi of wyx. Now, let me put pi psi check to be everything in the A packet, but it's, instead of them, take their dual, take the over duals, and then one can show that pi check psi is equal to pi of psi check. So this Aubert transfer of these representations is exactly the A packet attached to psi check. This is proved for classical groups. You need to have endoscopic commutes with induction, and this is proved for classical groups. Thus, the involution will send A packets to A packets. We note that the involution preserves non-singular supercuspidal packets. And these things are equal to identity, and this is elliptic as well. I mean, whatever gives us the parameter for a supercuspidal. Whatever gives a parameter for supercuspidal representation of the WF. It has to go to a cuspidal. Yes. Yeah. You know, there are these singular packets, and the singular packets means that there are discrete series beside the supercuspidal. You're staying away from them. So that would mean that both of these SL2D, SL2DC, and SL2A are going to go to 1. Those are singular packets. Now, the other generalization, which is really more in the sense of packets, L packets, is what we did. This paper that Hazeltine, Liu, and Bain Liu, Xiang Luo, and myself, we set up a conjecture which applies not to A packets, but more generally to L packets. Now, this generalizes in a different way what we did. So let me explain the conjecture. Now, G is equal, of course, it is done very generally, but let's assume G is quasi-split, connected reductive group over F. Assume LLC exists for G of F. let phi be an L parameter for G of f and phi sub phi be the corresponding L packet. Then the following holds. First of all, for any pi check in the dual of this L packet, pi check, as I said, dual may not be an L packet, so I'll just keep it like that. So this is the Aubert-Jelevinsky dual of the packet pi sub phi, which I'm going to write like this. For any of these and any nilpotent orbit in the geometric wave packet of this wavefront of this pi check, one has that is bounded by dBV of phi. Remember, phi was a L parameter, and we defined what O so phi is, and then you take the Wabash-Vaughan of that O must be less than that, and there must exist one representation pi check in pi phi check, so that the geometric wavefront set of it is exactly dBV of O. Okay, so this is the generalization that we have, and the best way to appreciate this is to check it on Arthur parameters, and Arthur parameters are those L parameters which are, remember I defined that infinitesimal character, W going to, phi of W and X was going to, let me go back to that. Yeah, here. Psi of, starting with the L parameter, Arthur parameter psi, the L parameter, phi psi, this is of course in the A group, this is the lean SL2 equal to phi of Wx and diagonal of this. This is the infinitesimal character of psi. Okay. So we will say an L parameters of Arthur type is if there is a psi, so that L parameter is phi psi, defined by that infinitesimal character. And the best way is to check it in this case. So, so let me take an Arthur parameter psi and assume that the L parameter is of the form phi psi. Again, recall that for the classical groups, we know that pi psi check is pi of psi check, and remember this check just changes two SL2s. Now, also note that if phi is phi psi, then pi sub phi is contained. This is the L packet which contains in the A packet. Now, if you do, of course, the duals, if you take the Jelevinsky dual of pi phi, then of course this L packet, when you do it, is going to be inside this A packet attached to psi check. And this is not an L packet, but it's a dual of an L packet. Now, recall that O sub phi is determined by the image of nil positive element under phi psi restricted to SL2 D of C. Now, O psi check is determined by the image of the nilpotent element under restriction of psi check to SL2 D of A. Now, but psi check restricted to SL2 of A is the same as psi restricted to SL2 D. So you will conclude that these two O psi check and O phi psi are the same. Okay, so this is when you have an L parameter of Arthur type, then you have O of psi check is equal to O of phi psi. And as a result, you will have that dBV of O psi check is exactly equal to dBV of O phi psi. In particular, this thing will also attain the same upper bound as psi check. This is a stronger version of it's stronger than Jiang's conjecture, because you will attain that upper bound in a smaller set. That's one nice thing about this thing. Let me now verify that this in fact generalizes the generic packet conjecture. Suppose psi is a tempered Arthur parameter, and psi restricted to the Arthur SL2 is 1. Or psi check restricted to SL2D, because these things switch. So psi check restricted to Deligne SL2C is equal to 1. Now let phi be equal to a phi psi check with the L parameter attached to psi check. This is an Arthur L parameter. Then we have phi x is equal to phi psi check of x, which is it belongs to psi check restricted to SL2D of C, and that is 1. That is one for any x in SL2 D of C. Therefore, O phi is just a trivial orbit. So when we start with one of these Arthur parameters, then Arthur type parameters, then we will conclude that that parameter for that parameter O sub phi is trivial. Take the parameter phi, which is a phi side check for some Arthur parameter, and then we will conclude that O sub phi is trivial. Now, if you take the dBV of a trivial orbit, you will end up with a regular orbit by our conjecture. So this means that this will be equal to this. Now, is the regular orbit, this geometric orbit which is attached to this. This O5 was the trivial one. This is going to be the regular one. So this is equal to the regular one. And therefore, you will conclude that pi is generic. So this is really a generalization of the conjecture in terms of the dual L packet. Now, there are other conjectures which which are of interest. So let me explain them. G is a quasi-split connected reductive group over a field F. Assume the theory of local Arthur packets for G of F as conjectured by Arthur. Assume that exists. Then a local Arthur packet is tempered if and only if it has a generic member. If you have a theory of Arthur packets, and then there will be, so being tempered in that theory is exactly having a generic member. This conjecture has a number of interesting global consequences. In fact, under some weak version of the local Langlands conjecture equality of L functions and automorphic L function, Artin and automorphic L functions, we can already show that, which is valid. Automorphic L functions and Artin L functions, when there is a theory, they are equal. That in many cases, they prove that they are equal over the Archimedean places, and naturally they are equal over the Archimedean over the unramified places. And the weaker version of this conjecture was proved in my Kyoto journal paper. So pi of 5 psi as a generic member, then it is a tempered packet. So this most non-tempered guys cannot have a generic one in there. Okay? If they do, they are tempered. So all right, and now when G is symplectic or quasi-split orthogonal, the conjecture is proved by Hazeltine, Liu, and Low. In a paper, they also answered some of the global consequences of the conjecture formulated in the Kyoto journal, which are due to Arthur and Clauzel, which are really Arthur and Clausel's conjecture. They demand that if you have a hospital representation, all its local components, almost all the local components are ramified, and they belong in here. Of course, being unramified is trivial, but they really belong to this smaller subset of the packet. And there are also some results about temperedness of locally generic cosmos. This is results are due to Hazeltine, Liu, and Low, and it appears in a new paper of them. They put it on arXiv. This is the title. They have many papers, as you know. This is the title of the paper, and you can go check it. They showed these global consequences, these whole issue of L packet and A packets, and I think I'm done. Thank you.